There are a variety of different data sources available for generating aggregate demand point information. And the first example that we'll be talking about is using US city data. And as mentioned in class, the city data really should only be used for labeling and not as the actual demand point. The reason is that the city itself might be much smaller than the actual population area surrounding the city. Typically, you might have lots of small cities that together make up a metropolitan area. So instead, using other sources of aggregate data that better represent the actual population is preferred. Those other sources, primarily zip code data is useful, three-digit zip code data for covering the entire United States. So in terms of examples, in terms of the city data, for just North Carolina itself, there's 739 total cities. If we look at, again, just for North Carolina, using the multiple OR function, we can restrict the US zip, three-digit zips to North Carolina. And if we do that, there's only 20 three-digit zips covering North Carolina. There's also county data available. So if we want the North Carolina counties, there's a total of 100 counties. For five-digit zip information, there is over 1,000 five-digit zips. So if I was solving a location problem and wanted to get adequate coverage for the entire state of North Carolina, it's usually good to, and say I was going to be locating 10 facilities or dealing with roughly 10 facilities that then are getting demands from throughout the state, then 100 times that 10 or 1,000 would be roughly the number of demand points that I would be interested in. So the five-digit zip data would be a good source. If I wanted to get a finer level of resolution, I could use the US Census block group data, and this is a much finer level of detail. And for the entire state of North Carolina, they have over 6,000. So this is probably too large a set of aggregate demand point data for the entire state. But instead, if you are doing a smaller area within a state, a metropolitan region, then it's probably the best resolution. And there's an example we'll get to in a minute that shows that. We can take this data though, and if we wanted to determine for the 6,000 points, what is the single location that minimizes the weighted person distance traveled for the entire United States? So this is the same kind of problem that we had solved previously using city data, and now we're using we're using just the North Carolina cities. I think a total of like 80 cities, and we found a location near Asheboro. And if you look at this result, you can see that it also is a location very near Asheboro. So even though we went from 80 or less than 100 city locations all the way up to 6,000 aggregate demand points, the accuracy of the location really hasn't changed much. I would argue this is probably slightly more accurate, but for the significant increase in data, it's probably not worth the effort. And for the type of location problems we've solved to date, the increase in size is not a difficulty. If we're using the mini-sum location, continuous location problem, large amounts of existing facility data is not a problem. But when we get to the discrete location problems that we'll be talking about, the different heuristics, then having too many points for existing facilities can greatly slow down the heuristic. And as you can see, in terms of the quality of the result, it doesn't really gain you much in terms of overall quality. That's why you really typically just want to use enough data as necessary. So it's very helpful to have, as shown here, a variety of different data sources. One of the reasons that the three-digit zip data was created, it's data that's not available like from the government. They basically just have the five-digit data, but the three-digit data was then created from that just so that you would have lesser numbers of data points. There's over 30,000 five-digit zips for the entire country and under 1,000 three-digit zips. So it's a nice reduction in the total number of zips, and it makes the especially the discrete problems much easier to solve, and you don't really give up much of anything in terms of resolution. In terms of top cities, in terms of population, this is something we talked about relative to using cities versus other sources of demand. Here I'm going to take the US cities that have at least 50,000 population, and I get the population, and then what I want to do here is just get the top 20. So since I want to get the top 20, I want to do the sortation of the population vector, and by default the sortation is from smallest to largest. So if I take the negative of that, it'll give me from largest to smallest. And then I'm taking argsort, so I get an index of all of the indices, and then I'm just taking the first 20 elements of that, applying it to then the names of the cities, and this is the listing of all of the cities. And notice that, as was talked about in class, Atlanta, which is a large city, doesn't actually appear in this list. It's actually the over 300 in terms of large size. So there's over 300 cities that are larger than Atlanta, even though the Atlanta metro area is much larger. For zip codes, first I'm going to look at all of the zip codes for the United States. It's actually close to 42,000 5-digit zip codes. I can then plot that. So I'm going to do in one line. Since I do these three things all sorted together as a block, instead of doing it as 3 lines, I can make my scripts a little bit more concise by just separating each of these with a comma. So I'm calling make map, so I get a map covering these sets of long lats for all the 5-digit zip codes. Then I'm putting red points, and then I'm labeling it as US. So I do that as one call, and I get quite a dense coverage of the entire United States, a little bit sparser in Alaska and Hawaii, and then Puerto Rico. If I do the same thing for 3-digit, and here I'm just looking at continental United States, I can do the same type of plotting, and here I get a much more sparse coverage. But this is the level of detail that I think is more than adequate if you're doing a nationwide type of location problem. You have over 900 different data points that you're looking at. And then the last example is looking at the Raleigh area. And previously the US government had metropolitan statistical areas, or MSAs, and they've added additional aggregations of metropolitan data. And one of the new ones is called the combined statistical area. And what it does, if you're previously with the MSA data, Raleigh and Cary was in a separate MSA, and then Durham and Chapel Hill were in another MSA. But since they're really neighbors of each other, for most types of analysis, you'd want to consider those together. So I think that was a problem that this new aggregation really does solve, because now with the combined statistical area, it covers Durham, Chapel Hill, and Raleigh, and all the outlying cities that are close to that area. So the information has been added to the US county data, and some of this information that we're going to extract, the first is the state and county Fips code. Fips is Federal Information Standard Code. I believe now it's actually called the ANSI code. The name of the county, and then this is the combined statistical area title. And I'm going to these are the first 3 elements, and then I'm going to extract only those that are part of the Raleigh combined statistical area. So I can do that by using the multiple OR function. And then I'm just putting enough information to be able to detect Raleigh in the CSA data. The entire name is actually longer than that, but that'll be enough to then select from the US county CSA title data all of the counties corresponding to the Raleigh CSA area. So this can be done in one command. It generates then those 3 pieces of data. The first thing is I can look at this. I'm going to take the string, and if you look at it, the string actually has 11 elements, so there's 11 counties in this CSA, and they all have actually the same title. So I don't need to have all 11 copies of it, so I'm just using the first string, and then I'm appending to it CSA. So when I do that, I define the string function to be Raleigh, Durham, Chapel Hill, North Carolina, CSA. And I'm going to use that when I plot it as a title for my figure. And I can also use it here when I call the matrix display function. And here I get a listing. Here's the name of the CSA. This tells you the data. It's the state, county, Fips code data. And then these are the names of the different counties. The 37 is the North Carolina Fips code. And then these 3 digits represent the Fips code for the counties. And again, as I mentioned, there are several counties throughout the United States that are labeled as Wake County. I'm sure there's lots of Lee counties, Johnson County. So you need to prefix the 3 digits for the county with the 2 digits for the state to be able to get a unique code identifier for a particular county. So with that, we can take these state county Fips code and then use it to look into the U.S. Census block group data and then get information for those counties. There's a total of over 1,000 census block groups area in the Raleigh, Durham, Chapel Hill, CSA area. So that 1,000 is sort of that good number to do different types of analysis. You know, that's enough that we actually are covering quite well the actual point. And here we can actually plot it. And you can see this is the Raleigh area. And when we solve this as a location problem, we can go ahead and do that. Let me just, so I'm going to call XY the location, mini sum location, and then my P points are actually the XY. My weights are going to be the population. Here I need to make it a vector. I think it comes as a column vector, so I'll take the transpose of it. And then I want to do miles. And I get that point to see where it is. I can do long lat to city. And I end up with a point that's a little under 5 miles west of Raleigh. So if I look at the underlying figure, for Raleigh, it basically puts it at a point right here in this middle of this metro area. I think based on the centroid for Raleigh, it's an area that's really close to the Crabtree Valley Mall area. So if you're basically serving the entire metro region, that maybe helps explain why they chose to build Crabtree Valley Mall at that location. If you look at it, it's pretty much the central location for the entire triangle. So it kind of makes sense in terms of that being a location. I have all these figures. I've done all these splitter. This is figure number 4. If I want to clean up and remove all of the figures, it's useful to use the command close all. And when I do that, it eliminates all of the figures. So it kind of cleans up my workspace. So next I would like to, and if I want to get rid of all these variables, I can do clear. And then also I can go one step further. If I want to clean up my command, I can do CLC, and that cleans all that up. And if you look at my version, I have these actually little buttons here that do all of that. This, for example, is clear everything. And if you look at edit shortcut, what it actually is doing is every time I hit that button, this macro, it executes all these commands. So it closes all my figures, clears all of the, and does the CLC command and a few other things. So it basically allows me to kind of, if I'm working and I wanted to start over from scratch, I can hit that one button and it kind of does everything. And I have a lot of other things. So if you use MATLAB a lot, it's pretty easy to just customize the toolbar by doing these different types of macros that can execute, and it can really save you time if you're going to be doing the same thing over and over again. For the UFL heuristics, the first one I want to talk about is the Ufl Add procedure. So in terms of our data, we're going to have the 5 cities along I-40, Asheville through Wilmington. And I'm just going to assume a transportation rate of 1, a flow of 1. So basically the cost is equal to the distance. So I can generate my variable cost and then my fixed cost. It's going to be different for each new facility. Again, that's one of the advantages of the UFL problem, is you can apply a different fixed cost at each site. Even if you are adding a fixed cost interactively using the ALA procedure, it really only works for having the same fixed cost every time you add a new facility. So the first step is to look at what first facility to locate. So first I'm going to create the set n, and my solution vector I'm going to set equal to empty. Set difference, anything with the empty set is just the original set n. And then I have a for loop, and in this for loop I'm going to look at all the possibilities 1, 2, 3, 4, 5, looking at the cost, and the minimum cost is for establishing a facility at I equal 3 with a minimum of 665. So I'm going to set my first new facility to y equal 3, and then when I do set difference I have 1, 2, 4, 5. I can basically do the same loop. So this is exactly the same code. It does the same thing. Here it found 1 having a minimum of 645. So I can take that 1, add it to my y vector, and then repeat the process. You can imagine this would be put inside a loop inside the actual code. Now with the set difference I have 2, 4, and 5. Apply the same loop, and here none of my costs are less than 645. These both are still equal to 645. So at this point I would go ahead and stop the procedure. So that's a step-by-step version of the add heuristic, putting it all together and writing it as a general procedure. Assuming that K and C were given as input, I can start off, set my cost equal to infinity, and run the code, and end up with a solution returned with the indices of where I'm going to be locating facilities, in this case 2 of them at 3, 1, and then a total cost of 645. All of that then is part of the Ufl Add heuristic in MATLAB. I can do that same thing. One additional piece of information that the heuristic gives me is this output argument x, which is a matrix that tells me which existing facilities are assigned to which new facilities. So the columns correspond to the existing facilities and the rows correspond to the different sites. So it says that the new facility at 1 is only serving site 1, and then the one at 3 is serving all 3 of these. So essentially, if you remember, this is Asheville, and that's served by 1 new facility, and then all of the other 4 cities are served by a city at, if we look up at our list of cities, the 3rd city is Greensboro. So Greensboro is serving Statesville, Greensboro, Raleigh, and Wilmington, and then Asheville has its own dedicated facility. There's also a Ufl Drop Procedure, and it's similar to the add procedure. The only difference is that we start off, instead of y being empty, we start off with having facilities at all 5 sets of locations, and then for that we calculate a total cost of 850. And now what we're doing is looking at, if we drop one of the facilities, if we take the set difference between y and I, which is then indexed through all of our existing facilities, what is then the resulting total cost? And we do that, and it turns out that 720 is the biggest reduction we can get. So what we're doing here then is eliminating 2 from our list of new facility. So we've dropped 2. We can do that again. Here we get 645 twice, so we could pick either 4 or 5. So assuming we pick 4, we're left then with 1, 3, and 5. And then repeating, here nothing falls below 645. So we end up with 1, 3, and 5 as our solution. So in looking at that, you can see it actually is a different solution, even though the total cost is the same 645. We got that using 3 facilities. And the difference is that the facility at 3, instead of serving 4 cities, now Wilmington can actually be served by its own third facility located in Wilmington. So both Asheville and Wilmington have their own facilities, and then the one in Greensboro is just serving the 2 neighbor cities. And this and the add actually have the same total cost. Third example is using the UFL exchange improvement procedure. And for this improvement procedure, we can start with a solution from our Ufl Add heuristic. And then the exchange procedure works by, given that y as an input, it calculates the overall best cost as that value, which is equal to 645. And then I'm going to set TC prime, and in MATLAB I use 1 to indicate prime in this context. I'm going to set TC prime equal to infinity. My done flag for my repeat until loop, since I have to use a while, I'm going to set the done flag to false. So the first time I go into my while loop, it'll be true. And I'm going to keep repeating. And what I'm doing here is looking at, for all of my new facilities, relocating it to one of the available sites and seeing if there is a reduction in cost. So I can go through all of that. And it turns out if I switch and have facilities at, so I came in having one at 1 and 3. Well, it turns out in terms of this exchange procedure, it was able to actually find an improvement by keeping the facility at 1, but then the one that was at 3, moving it to 4. And in doing that, it reduced it to 600. So that's an example of how the Ufl Add procedure, since it's a greedy procedure, the biggest, the smallest total cost for a single facility was at site 3. But then once we added the second one, it was actually beneficial to move the one from 3 over to 4. That's like the example for best warehouse locations. The single best location was in Bloomington, Indiana, but then as soon as you went to having 2 covering the United States, one went to California, and then the one in Indiana moved away from Bloomington. So we're kind of seeing the same thing happening here in the discrete space. That's why you don't want to typically, unless computational or for whatever reason there's some reason you can't run the exchange procedure, but when all possible you should use the add construction procedure and the improvement, and also include the drop procedure. And all of that is combined in the next example, which is the Ufl Hybrid Algorithm, which does essentially that. It starts with the add solution, then looks at applying the exchange procedure to the procedure. If there's a reduction in cost, then it goes and from that solution. So this is an example where it's using the Ufl Add procedure, but instead of just 2 inputs, it's supplying it with a starting point. So instead of starting from no facilities and adding 1, 2, 3, 4, it starts from y as an existing number, which is the value returned from the exchange procedure. And then it looks to see, is it profitable to actually add from that starting point? It also looks at, is it profitable to drop a facility from that point? If so, go ahead and do that, and then repeat the exchange procedure, and then try to add, try to drop. If any of that results in an improvement, then continue the procedure and so on. So it keeps doing that until there is no further improvement. So I can go through the whole procedure here. And here I end up with 1 and 4 and 600. So that first exchange could not be improved upon, which for this small of a problem, you wouldn't really expect that it could be improved upon. Next example is the p-median procedure. And for this p-median procedure, one way of doing it is just to use the Ufl Add procedure and basically just make all the fixed cost equal 0, and then just keep adding procedures until you reach a total of p procedures. So we can start and do it this way. We can set p equal to 3, call the Ufl Add procedure, and it has built inside of it the option to have this 4th input argument, p, and what it'll do is it'll just keep adding until it reaches p. So it's not looking at seeing is there a further reduction in total cost. It just keeps going until p is reached. So with that, the add procedure picked 1, 3, and 5. We can run the exchange procedure. on that solution, we get this. Notice that what is returned for X is a sparse array. If we want to see it, we can call mDisplay, and it displays this solution. And here, if we want to see, then notice the total cost is 145, and the reason is that we're not including any of the fixed cost. So to make it comparable to the UFL solution, we can add the second term, which is the sum of the fixed cost, and we get our $645 total cost back. We can also create a p-median solution procedure given P and C as input. And then this is a function called p-median that's part of MATLAB. And we do that, we end up with a total cost of 145, because in this procedure there's no notion of fixed cost. But as we saw before, we're really getting the same solution, minus the fixed cost. And then the last thing I want to talk about is the difference between the bottom-up and top-down analysis. So for homework 3, question 3, we did a bottom-up analysis where we had information about the number of truckloads and the transportation rate. And then with that, we calculated the distances and got this distance matrix, which is a 3 by 3 distance matrix. And then from that, I looked on Google Maps and got the actual road distances between the Detroit, Gainesville, Gainesville, Memphis, and then Detroit, Memphis. So looking at those 3 pairs compared to their actual distance, I calculated the mean of that and got 1.21. So then for estimating the mini-sum location, the optimal point, I can solve that. And notice the weights here are, since it's minimizing the distance, the great circle distance, I'm taking the circuity factor and applying it to my weights. Since everything gets multiplied together to create the total cost, it doesn't really matter if I put the circuity factor here as part of W or if I multiply it times D. Either approach is equivalent. And then I could look at the XY location for Cary, North Carolina, and get that. And then I can get the total cost for Cary. And the results are then displayed using the variable display function from MATLAB vDisplay, where you have the names of the variables in the workspace. And in this case, you can have the difference actually executed. And then when that executes, it actually displays as a nice table. And in this case, it shows that there's an increase of just under $38,000 associated with locating in Cary, as opposed to the optimal transport focused look. We can also do a top-down analysis where we're estimating a nominal transportation rate using the total cost for Cary. So this would be the situation where there's already a facility at Cary that generated a certain amount of total cost, and then we can divide it by estimates of, and if we take the truckloads and assume 10 tons per truckload, that would convert into this many tons per year. So that many tons per year times our distance traveled, great circle distance, times the circuity factor, would then allow us to estimate a nominal transportation rate of $2 per mile. So instead of being given that in the bottom-up analysis, we're actually inferring a nominal transportation rate of $2 per mile. And then since we're already in Cary, we can see, well, what if we, instead of locating in Cary, we locate to another location? We can solve that and then display those results and see that the optimal location would save us just under $38,000. So in this case, we're in Cary, and if we were instead going to the optimal, we would save $38,000. The difference is that the top-down analysis assumes that we have an existing operation, that we have total cost information from. What we don't have are all the details, or we maybe have it, but it might be difficult to actually calculate all of that. So instead, we calculate a nominal transportation rate and then use that to determine an optimal location, and then are able to estimate what the savings and total transport cost would be. When the bottom-up analysis, this would be more appropriate if there doesn't exist any facility and we're starting essentially from scratch. And knowing the number of truckloads and the transport rate, then from that we can actually determine the optimal. So depending on the availability of the data and what type of problem you're solving, both bottom-up and top-down are methods that are used in practice in logistics network design and analysis.